Hello everyone. In this video, I'll talk about gray codes, how to obtain the gray code for a binary number and vice versa, and their applications. Gray code is a sequence of patterns in binary numerals where two consecutive patterns differ only by one digit. An important thing to note here is that gray code is not a numeric sequence in binary, but it's a sequence of patterns. Here is the binary representation of decimal numbers 5 and 6. In binary, it's 101 and 110, while in gray, decimal number 5 and 6 are denoted by patterns 111 and 101. Note that in binary representation, bit 0 and bit 1 have to change for transition from 5 to 6. If we observe at gray code, for transition 5 to 6, only one bit flips. That is bit 1. The table in this slide shows the binary representation of decimal numbers from 0 to 8, and then we have corresponding gray code for these binary numbers. In this gray code sequence, we see that every next number differs from the previous just by one bit flip. So here this bit 0 flips from 0 to 1. Over here from 1 to 2, bit 1 flips from 0 to 1, and the same thing we observe across the whole table. Here is the algorithm to find the gray code for a binary number. Let's look at the steps. First, we write down a binary number that we want to convert to gray. Then we right shift the number by one position and write it below the original number. And then we perform a bitwise XOR of the two numbers. Let's look at an example. Suppose we have a binary number 10010 and we want to find the gray code for this number. We take this number and we right shift it by one position and write it below this. So this is the shifted version. And then we XOR each of the bit positions. 101, 011, 000, 101, 011. And this 11011 is the gray code for the binary number. Here is the Verilog implementation of the algorithm to compute the gray code for a binary number. So we have binary number as input and the gray code is the output of this module. We take a binary number, we shift it by one position and we XOR it with the original binary number to obtain the gray code. This slide shows an alternate implementation of the algorithm. The previous implementation uses shift register and XOR gate, while this implementation uses only XOR gates. Now let's understand how to convert a gray code back to corresponding binary number. Here is the algorithm. First, set the MSB bit in binary number to same as the MSB of the gray code. Then, to compute the rest of the bits in binary number from MSB minus 1 to 0, we follow this process. The nth bit in binary is XOR of all the bits from MSB to position n in gray code. Let's look at a graphical representation of the algorithm. Suppose we have a gray code 11011. To obtain the corresponding binary number, first, we copy the MSB bit from gray code to binary MSB position as is. So this 1 comes over here. Then for the rest of the other bits, we follow the algorithm described above. For position 0, we XOR bit 4, bit 3, bit 2, bit 1 and bit 0. For 1, we XOR bit 4, bit 3, bit 2 and bit 1. For position 2, we XOR bit 4, bit 3, bit 2, and for position 3, we XOR bit 4 and bit 3. So 10010 is the corresponding binary for gray code 11011. Here is a Verilog implementation of the algorithm, which converts gray code to corresponding binary. Gray coding is used in digital communication during digital modulation process to facilitate forward error correction in transmission. For example, in digital modulation schemes such as 4-com, 16-com, the signal constellation diagram is arranged so that the bit patterns conveyed by neighboring constellation points differ only by one bit. So if we look at these constellation points, every point differs just by only one bit from its neighbors. By combining these modulation schemes with forward error correction capable of correcting single bit errors, it is possible for a receiver to correct any transmission errors that cause a constellation point to deviate into the area of a neighboring point. This makes transmission system less susceptible to noise. Let's look at another application in asynchronous FIFOs. Gray codes are preferred to code read and write counters at clock domain crossing in digital asynchronous FIFO circuits. This is important to avoid error due to metastability. Let's understand this. In FIFO circuits, when we increment gray code based read and write counters, only one bit transition occurs while other bits remain stable. These counters are transferred from write domain to read domain and vice versa. If the destination clock domain latches data during metastable state, only one bit is uncertain, and the destination domain reads the counter value, either an old counter or a new counter. This technique significantly reduces the probability of errors due to metastability of the flops at clock domain crossing. That's all for this video. I hope this helps you to understand gray codes, their properties, and applications.